Every second of every day, NASA's satellites beam down a continuous torrent of telemetry, continuously capturing highly specific measurements from orbit, tracking atmospheric aerosols, sea surface temperature gradients, global ice thickness measurements, and shifting ocean levels. Getting these readings out of the sky is a solved engineering problem. The real challenge is figuring out how to permanently store and organize all of it once it hits the ground. Without a massive, mission-critical architecture to receive and distribute this incoming feed, multi-billion-dollar orbital sensors are effectively useless to the scientific community. Go back to the early 1990s. NASA's engineering hubs realized they were on a collision course with a massive data bottleneck. New Earth-observing missions like Terra and Landsat were scheduled to launch, and mathematical models projected they would generate data faster than any existing enterprise system could physically store it. Engineers had to build a petabyte-scale archive using only early 1990s processing iron and primitive storage arrays. To manage this volume, NASA moved away from traditional centralized storage, building a decentralized architecture called the Earth Observing System Data and Information System, or EOSDIS. Instead of dumping everything into one central server farm, NASA engineers rejected the standard monolithic database model. They broke the architecture into a federation of specialized independent nodes called DAACs. Each manages a strict domain: atmospheric chemistry, cryosphere, ocean color, or precipitation. Though geographically separated, every file is cataloged in a unified index, the common metadata repository. This extreme geographic decentralization solved the capacity crisis, operating as a functional precursor to modern cloud computing decades before the term existed. But ingesting those raw satellite packets at the DAAC downlinks required heavy computational force. NASA relied on enterprise computing power: SGI IRIX servers, SPARC systems, and IBM Power machines. These machines chewed through the raw level 0 telemetry, mathematically converting it into calibrated, gridded formats like HDF files before they could be written into long-term storage. All that processing power still doesn't answer the primary question: where does the data actually live? This diagram shows the EOS disk storage pyramid. The top tier uses high-speed RAID disk arrays for active processing and near real-time workflows. But the vast majority of data drops into Tier 2, a deep archive layer built entirely on magnetic tape. Tape is often considered a dead technology, but for deep archives, it vastly outperforms hard disks. It requires almost zero power to maintain, scales effortlessly to the exabyte level, and preserves data for decades without decaying. The physical reality is a network of automated tape libraries operated by robotic arms, fetching and returning petabyte-scale cartridges 24 hours a day. Tape is the physical bedrock that keeps the cost of decades-long scientific memory economically viable. To see how fast this federated architecture performs today, we can track a live data query. Imagine a climate researcher in Brazil needs to study historical canopy health in the Amazon basin. They request 2 decades of data from an instrument called MODIS. Almost instantly, the assigned DAAC retrieves the tape, processes the query, and delivers 20 years' worth of precise wildfire hotspot coordinates directly to their terminal. That seamless global retrieval works in minutes because the indexing pipelines were engineered to survive a massive data deluge 30 years ago. By 2005, EOSDIS held 3 petabytes of archived information. Today, it stores tens of petabytes of continuous atmospheric and oceanic records. And it expands with every passing second. With every satellite orbit, new telemetry drops into the downlinks and is written to the tape arrays. This is a globally accessible, continuous archive of the Earth. EOSDIS provides a baseline of our planet's history, ensuring researchers can see exactly how the environment looked decades ago.